Okay, let us begin our today's seminar, and our today's speaker is Evgenii Nikishin, and we'll give us a talk about hierarchical methods of reinforcement learning, also known as options learning or micro-actions learning. So probably one of the most promising trends in modern reinforcement learning, which allows, at least in theory, to reduce the horizon of planning that is assumed to solve the most crucial problem in modern reinforcement learning.
Okay. Thank you for the introduction. I'm going to discuss hierarchical reinforcement learning, but before that, let me briefly recall the reinforcement learning setting. You're given a markov decision process. You have an environment that is described during each time step as a state. You have an agent that observes an environment state. Agent can produce some actions that lead to some rewards and new state. And goal of an agent is to maximize total cumulative discounted reward. Discount factor is added to make preference on current rewards, but not too far. There are a bunch of standard approaches, but before we go to them, I'll need two functions. First of them measures the value of some state following the policy pi, and second of them measures the quality of action A following the policy pi in state S. These functions obey some properties. For example, you can rewrite Q function in terms of V function and V function in terms of Q function. Moreover, they obey Bellman optimality equation. We are going to be interested in Bellman optimality equation for Q function. And first, simplest method for solving reinforcement learning is Q-learning, and that's simple application of fixed point iteration algorithm to solve following system of equation. And we can iteratively rewrite this as follows. Alpha k times xk minus f xk. That is, Q-learning is just application again of fixed point iteration algorithm. Another any questions so far? Okay.
It seems you missed gamma in the last formula.
Yeah, sorry. Gamma should be here. Yeah. Another common approach is to parameterize policy directly and perform gradient ascent with respect to its parameters ascent, because we maximize discounted reward, and this result is known as policy gradient theorem. And I want to prove it right now because it's very important to understand the anatomy of this policy gradient theorem. We're interested in taking the gradient of this. For simplicity, I'll assume that first state is fixed. Then, using expressions from slide earlier, we can rewrite V function in terms of Q function. That's gradient. V times Q function. Again, we can rewrite Q function in terms of V function. yet. It is just a writing of equations.
S and the S0, is it the same thing?
Yeah. Sorry. S0, sum of times reward plus gamma v pi over S0. Now we can move gradient into the summation. We obtain sum over A, gradient of pi, times function plus pi reward function does not depend on policy parameters, thus it will be 0, gradient of it will be 0, and it will be sum over S1 times probability of reaching state S1 from S0 A times gamma times the gradient of value function of P. Okay, is it clear for now?
No. The gradient is taken with respect to what parameter?
We parameterize, okay.
Theta?
Yeah, we parameterize policy, but to simplify the notation, I didn't write all this stuff here. P equals to P theta, and we are taking the gradient with respect to theta. Okay?
So V function doesn't depend on theta. Why
It does depend.
Why you put gradient?
It does.
It does.
Implicitly,
It does depend.
because it depends on the policy.
Well, we take gradient of the function from the very beginning. Yeah.
Mm-hmm.
Okay. And a last thing to note, that here's the gradient of the function, and here's the gradient of the function, but in next state. Okay.
And where the sum over R?
R, it does not depend on policy parameters, and thus we can this distribution marginalize. Yeah.
So we skip the term which depends on R.
Yeah.
And then the next term doesn't depend on R, so the joint distribution over S1 marginalizes
Yeah,
the
exactly.
distribution over S1.
Okay, and why you haven't taken the gradient of pi for the second pi?
This is just gradient of product. It equals to gradient of first term times second plus first times gradient of second. Okay.
You mean Q function?
This is the gradient of pi times Q function plus pi times gradient of Q function.
Okay, and the last part?
And the gradient of this stuff. Yeah, gradient of this stuff equals to this.
Where's the gradient
It's equal
of
sign,
Q?
not minus.
Again,
The gradient of Q, where?
this is the gradient of the function.
Yes.
Ah, this is equal sign.
Yes,
It's not
yes.
minus.
Where does the minus?
The second line.
Yes.
The second-
Oh, sorry. It equals.
Equal.
Sorry for confusion.
So
And why P of S0 equals to 1?
Again.
Left hand.
This is for simplicity. Again. Question.
This was the question. Why P of S0 equals to 1?
This is just for simplicity.
Okay.
Also, you have a typo on the second line. V of P of S1, not S0.
Yes. Okay. And last thing to note is that this is the gradient of the function, and this is the gradient function, but in the following step. That is, gradient is rewritten recursively. Let me write something. This is the gradient of I times cofunction of pi. Now we add two summations. First of them over all states, second of them over all over recursion. And here we times we multiply by probability of reaching state S from state S0 in k steps following policy pi. Let me explain a little bit. For k equals 0, with probability 1, we reach state S0, and that's this term. For k equals 1, we make one action, produce one action, leading to P of A given S0, and multiply it by probability of dynamics. That is, it is the probability for all states of reaching state from S0 in one step.
Right.
Okay, and that is basically
Wait.
okay.
But that's
Okay.
not all.
Also down.
So this is the probability, and what's next? So there was gamma times gradient of V.
Gradient of V is rewritten recursively, and that's why we obtain this summation over k.
And there is gamma.
Gamma is here. It's
Still not clear.
okay.
Wait, gamma should be in Q.
Gamma not should be in Q. It's here. Let me write what is it. Well, make something like this. This is sum over S of so-called stationary distribution of Markov decision process times this guy times cofunction. And that is exactly a normalized version of this sum over S of this. This is the sum of k equals 0 to infinity. Probability of reaching S pi in k steps. Okay?
Yes.
Okay?
And this is the stationary distribution of Markov decision process?
Yes.
Given the policy pi.
Mm-hmm. Oh, I guess. It's
That's an important issue.
Yes.
But still, well,
Mhm.
I don't know, maybe it's clear for everybody except me, but for me it's still unclear why this expression gives us stationary distribution. Can you justify it? Maybe we should check some kind of detailed balance equation for that.
I don't think that a proof of this fact take, I guess, 10 minutes. I'm not sure whether we want to check that this is exactly stationary distribution, but you can trust me.
And have you checked it? Have you checked
Yes, yes. That's by definition stationary distribution. Well, everyone writes that this is a stationary distribution of the math decision process.
Well, no. the definition of stationary distribution is different. I think I suppose it can be written in this form, but this is not definition of stationary distribution. That's why I was asking.
But it is some limits frequency of appearing the state S following the policy pi in this market decision process. I agree. Do you agree?
I would, but I'm still concerned about gamma to the kth power. This is something strange. If it were not gamma, I would agree with you.
But let's delete it.
Okay.
Okay. Now we use the log derivative trick to obtain expectation over S and over A. We multiply this and this by pi, and thus we obtain something like this. Okay. And times gradient of logarithm of pi a given s, and again times co-function of s pi. Okay, I guess that's pretty simple.
I would still say that we should multiply probabilities by gamma in order to obtain stationary distribution. Gamma should be included into Q. This is I think my motivation, because we need somehow to sum over all our rewards, right?
Okay.
For example, we know that we obtain some reward given by Q function if we're in the state S and follow policy pi, right? Now we know how many times we will find ourselves in the state S, and we should sum all these rewards with a discounted factor gamma. This is why it appears. So it should not show the rate of times when we are in the state S. This is why when you compute this at of S function, you should not take into account gamma. You should take it into account when you multiply it by Q.
Here's my argument. Do you agree that all of these quantities are not bounded? Well, this is not bounded. This is okay. This is not bounded, and if we do not add gamma in power of k, this thing will diverge.
Because we sum up to infinity.
Yeah.
Sure. I agree with you. The only thing I'm not agree with you is how you compute mu of s, or e of s. Because you claim that this is stationary distribution. My claim is that this stationary distribution should not depend on gamma. Your reward should depend on gamma. Your total reward should depend on gamma.
Yes.
But not stationary distribution. And when you define the stationary distribution, you use gamma, which you should not.
Yeah, it's very strange that the gamma appears in mu, whereas the reward does not. I mean, the stationary distribution is
Okay,
just for the...
let's discuss
There
it
should be
afterwards.
gamma, but this distribution, I think, people always, by some reason, call this distribution a stationary distribution, but I don't know the reason why they call it this way. But if you write this proof in a full way, you will see that there should be gamma in this mu.
But then this mu is not stationary distribution.
Yeah,
You may
probably-
denote it.
Nah, that's a bad name for this distribution.
Maybe people in RL, by some reason,
Stupid.
call this distribution stationary.
Actually, if I'm not mistaken, by definition it's called like discounted frequency. Blah, blah, blah.
Discounted frequency, I fully agree. This is discounted
that's-
frequency, but not the frequency itself. Discounted frequency.
Okay,
Okay, let us call it discounted frequency, and then everybody's happy.
okay. And using the log derivative trick, we can rewrite it as an expectation of as a comes from pi, gradient of logarithm of pi of a given s times the co-function.
Wait, but pi is only distribution over actions, not states. When you write S and A distributed as pi, that's wrong.
But our actions, our policy induces the distribution of states, because it influences the dynamics of the system.
This is just
This is
shortcut.
the first,
This is just notation.
Oh, you could just
Okay.
write another line of S distributed as...
the best
Are
thing
you
is
happy?
that
Okay, okay.
Okay.
Just call it discounted expectation.
And okay, how do we optimize this thing? Then we just sample like Monte Carlo estimation. We do like 1 over n t equals to 1 through n approx t t t t. And one thing to note here, that if we close cofunction, this is just maximum likelihood estimate of our state action pairs. But when we multiply it by cofunction, we increase weight of good state action pairs and decrease weight of bad state action pairs. Okay? So policy gradient is just weighted maximum likelihood estimation.
Okay, if there were not any Q, then it was maximum likelihood estimate for what? For the policy that which describes our current actions?
Yeah, we. I'm not sure whether it will work well, but yes, I guess that's it. Because then all our state action pairs are equal in terms of reward.
Yes.
And we just maximize the likelihood of parameters for which this state action pairs occurs.
So we have a sequence of state action pairs,
Yes.
right? And we try to, in some sense, to restore the policy which produce this
And
state action pairs.
and
And
that's
if we do it using maximum likelihood estimation, then we obtain exactly this maximum likelihood estimate
yes.
with ignoring Q.
And that's basically the simplest method for imitation learning, but it's out of scope of our talk. Okay?
I wonder, so now assume that we have a sequence of state, action, reward
Okay.
triples, right?
Uh-huh.
So now we're not interested in describing well the given sequence. We're interested in finding policy which produces the maximum possible reward. And one possible way of doing this is to use this weighted maximum likelihood estimate. When we
Yes.
concentrate on those actions which produce high rewards.
Okay.
Right?
Okay.
So this policy which we will learn will not describe good the observed triples. but it will probably describe good policy for future actions.
Yes.
Good. So this is some kind of intuition of what's going on.
Okay. That was the recap of standard reinforcement learning approach.
So to understand right that there are two main ways of solving reinforcement learning. One
Yes,
way
exactly.
is pure learning and its possible relations.
Yes.
Another way is policy gradient learning.
Yes, yes, exactly.
But this is the mixed approach. Here you have both policy gradient and Q function.
Yes, okay. I haven't specified yet. Up to now, we don't know co-function, and we can either use its Monte Carlo estimates. That is, if we have our episode, if we have time, and for some time step t, we can sum up our following rewards to obtain Monte Carlo estimate of co-function. Okay? And instead, we can use another neural network and to learn this co-function via, again, Q-learning algorithm and its modifications.
And this is mixed approach.
Yes.
Right?
Mm-hmm.
So you will parameterize both policy and Q function, and this is called actor-critic.
Mm-hmm.
Is it correct?
Yes.
Good. I always dreamed to find out what is actor-critic, so now I know.
Okay. Someone in the hall is happy. Now, let me move further and introduce hierarchy. Any questions so far? Okay. Now let me move to hierarchy. Classical way to introduce hierarchy is options approach, and option is a tuple of 3 components. First component is a subset of state space where it can be initialized. Second component is option policy upon primitive actions or micro actions. And third component is probability of determination in a given state. When current option is cancelled, is terminated, we give control to meta policy upon options, which chooses next option to execute, and executes next option. Okay, and as an example, you can consider navigation task. When you see nothing in front of you, you can move forward until you reach a wall, for example, when you reach the wall, you choose another option to execute.
What's the difference between options and actions?
Options is definition is in some sense macro actions. You have actions that is primitive actions. Well, option is macro action. Action is micro action. Okay.
Give example.
Okay.
I think the best way of thinking about options is that
The sequence of options.
each
Sequence
option
of
defines
actions.
specific policy,
Okay.
and you switch between different policies.
Okay.
And you may learn simple policies by using these options.
Excuse me?
Yeah.
What is the motivation? We like use different policies for different states. Why we can store
I'll
this
talk
information?
about motivation. Okay. But very basic motivation is following. When the best intelligent system that we know is human. Okay, and when the human plans or produce some actions, he does not think of in terms of what muscles should it use, but it thinks in terms of, oh, I want to drink water, for example.
Crazy illustration.
When you imagine options, you can. Your hope is that using them, you plan on a longer horizons. Okay? And here we come to probably most important slides of current talk. Well, if we were given good set of options or meaningful set of options, I don't specify yet what does mean a good set of options. We will obtain all of this nice stuff on slide, like we will grant smarter exploration, thus we will increase sampling efficiency. Probably good options mean that it is interpretable options, that is we will be able to understand motivation of agents to produce some actions. But and there are very well-known problem in reinforcement learning that policy itself produces its data to fit, and that's why reinforcement learning agents is extremely harmful in terms of overfitting of local optima. And I wanted to show you a video, fun video. This is I guess dog, and it's tasked to move to the right as fast as possible. And here's probably some of you already have seen this video, but I'll show you. And this way.
Design problem?
Huh?
Maybe it's problem of reward design.
Yes, that's for local optima. Agent found another way to maximize their reward. I guess during training, due to stochasticity, it just for some reason flipped on the back, yeah. And when it's already flipped on the back, it should somehow maximize the reward. And that he found a way to maximize the reward, and that's an example of overfitting in reinforcement learning.
And why is it bad? So it seems like a good solution.
You can make better.
Why this is overfitting, but not the like environment problems?
Because policy itself generated its data to fit, I guess.
Welcome to moves.
Yeah, it kind of generalizes. I mean, it's poor local optima, that's right,
Yes,
but I wouldn't call it
poor.
overfitting.
I agree that this is poor local optimum, but again, my claim is that policy itself produced.
Yes, sure. But was it the sole source of this issue? I mean, why would it, like, evolutionary approach find the same solution?
Again?
Well, imagine you're doing just random search,
Okay.
lots of random search, and it just happened that the model at some point decided to flip over and run on its back.
Okay. Okay.
So this is not the problem of the model learning on its own samples.
Yes, I guess that's fair point. That's I don't know, general problem in reinforcement learning, I'd say. And but okay.
Exploration. If you don't use epsilon greedy solution, you have the exploration possibilities. So
it's
generally you
problem.
shouldn't be stuck in the local optimum.
Tell this to Australian animals.
That's exactly example of bad exploration-exploitation dilemma. Bad example of not solving exploration-exploitation dilemma properly.
So yeah, I think everything's
Okay,
clear
okay.
here. Let's proceed.
But here's what would happen if we have good options, but at the very beginning of learning we are not given these good options, and there are some arguments of that. First of them is that there are optimal deterministic policy in Markov decision process. It's a well-known fact. And that means that asymptotically we don't need any hierarchy. We need just a flat policy on primitive actions, and it will be optimal. Second argument is that it can be harder to solve MDP with options from scratch instead of just solving MDP, just because we introduce a large amount of parameters to our model. And thus I claim that most important application of options is transfer of knowledge from well, if you want overfit on your data, you'll be able to transfer to similar Markov decision processes. And that's why I think that most important application of options framework and in general hierarchical reinforcement learning is transfer learning. Probably some of you have comments or questions on this, because currently there are not too many successful approaches to learn options, and none of them grants better sample efficiency in learning in single MDP. None of them is better in terms of solving one MDP than usual algorithms.
That's quite sad.
Yes.
One could expect that due to the options, we should increase the efficiency of reinforcement learning because we shorten the horizons.
But not much working yet.
Well, you also introduce more stochasticity, and it's not helping.
Probably yes, and quite simple argument that larger number of parameters you should train. Yes.
And what is the transferring idea? We will just transfer good options to the new environment.
Yes,
right?
yes. You have two similar MDPs, and you learn some policy in the first and use it somehow in second. Not to train policy in second from scratch.
But we need to retrain like these micro policies.
Yes. No. Ideally, we would like to train only meta policy. Primitive options will stay the same, but we retrain only meta policy. Yeah? And that's our hope. Okay. Now we move to the first algorithm that learns options end to end, and there will be a quite messy notation, and if you're confused or feel lost, don't hesitate to ask questions. Extension of our value function is the following. First of all, we introduce a value of option in some state, is just the weighted average of another cofunction of 3 arguments. This cofunction is quite similar to original cofunction. If we won't have here omega, then it would be just the function. Okay?
Can you tell us what is large omega for stands for and U stands for?
Again? I didn't hear.
Notation. Can you explain the notation, please?
U, it's just notation. I guess authors call this U utility function, and this function have index omega because it's a cofunction of measure of quality of options. Okay.
And options and omega have the same first letter.
Okay. Now instead of v function here, we have u function, utility function. That is, intuition behind it is as follows, is following. If we do not terminate our option, that's just co-function of value of this option, but in following state. If we terminate this option, then it's average. This is the average value of all options.
To which we can switch
Mm-hmm.
at the state as prime.
Prime, yeah. Again, if you feel lost, please don't be shy. And okay, this function is quite similar to original function, and that's why we can learn it by simple modification of co-learning. We can write Bellman optimality equation for this co-function with index u, and then apply standard co-learning approach. Main contribution of this work is gradient with respect to parameters of micro option policies and termination functions. I'd like to recall that we're interested in learning option policies and termination functions for all options and meta policy. And main contribution of this paper is gradients with respect to option policy parameters and option termination parameters. And as you recall, this is maximum likelihood estimate, but weighted on how good this state action pair is. This is quite similar. We increase the probability of good state action in option omega. Also, beta is termination function, and that is we try to make good options to have a larger length. Okay. That's main contributions of the paper, and now we move to experiments. Does anyone have questions here? Okay.
Excuse me?
Yeah.
Don't you somehow parameterize beta?
Yeah. It is parameterized, but I didn't want it to add another index here and here because notation is already too hard.
What is this, like neural network? Or
Yes, it's neural net.
Could you please clarify why the first equation means that take better primitive actions more often inside the option?
Well, for each action you have its co-function with index u.
Yeah.
And some of them are larger, some of them are smaller. And if you have taken, okay.
I was confused with the term primitive actions. By primitive actions, you mean just standard actions.
Yeah.
Excuse me, once more. And how we train like meta policy of choosing?
Meta policy is epsilon greedy with respect to co-function. This co-function. Okay. And now we move to experiments. We have 4 rooms domain. Starting position is here. Goal position is here, and after training options, 4 options, we obtain following termination probabilities. The brighter is large termination probability, and well, it's so interpretable, but but you can visualize intentions of options. You can visualize where it does terminate, and that how you can somehow interpret intentions of agent. Next experiment. In next experiment, they applied option critic with 4 options, with 8 options, and 2 non-hierarchical methods. As you can see,
Yeah, that's a question.
yeah.
And what goal did we have during training on
Again,
forums? What goal do we have?
we want to move from this cell to this cell, and
Making the least possible number of moves.
yeah, we receive in all other cells reward 0, and in this cell we receive reward 1, and due to discount factor, we want to move as fast as possible to this goal.
Start and finish rooms fixed?
Yes. And in this scenario, as you can see, not the best visualization, but as you can see, non-hierarchical methods solve this task quicker.
And this is explainable.
Yes. But after 1,000 episodes, goal location is changed randomly, and hierarchical policy is able to discover this much faster than non-hierarchical, and solve new task in better way. Yeah,
Nice.
and that's I guess example of success of transfer of knowledge.
How do you build the options?
What do you mean by that? It's just 2 neural networks.
No, well, I mean that.
They are learned from scratch.
Okay. I might be misunderstood. So options are some policies between which then you will choose.
Yes.
Okay. You have 4 options. So you build them one by action.
No. You when you initialize your agent, you have for each policy, for each option policy, 2 neural networks, and then you simultaneously train it via gradient ascent. With this gradient. Of course, in practice, you do not have a separate neural network for each option. Some shared features are presented, but high-level idea is following. Okay.
Excuse me, one
Yes.
small. Does authors use the same network architecture for interpretability and their own algorithm, or they use like smaller policy networks for some?
I guess comparison was fair. Okay. It would be unfair to make to make.
But it like unfair, so since you have 8 neural networks, we see 1.
Well, it's not. As I said, you share the features between them. That's basically it's two neural networks. Okay. And if there are no questions, I'll move to second algorithm. It won't be too hard. This algorithm is applied exactly to make a transfer of knowledge, to make to solve multitask multitask reinforcement learning. Consider you have a set of marker decision processes. Each of them shares action space and shares some subset of state space. For example, you can consider a robot that observes different tasks. First task is to move as fast as possible. Second task is to move from this location to that location, etc., etc. Our actions is to apply force to some of its arms, etc. But arms itself is a part of state space. Okay. Then we will consider following pipeline. In the first very generic MDP, you will obtain a bunch of diverse skills. Then, on top of these skills, in following MDPs, policy on top of these skills are trained. Yeah, pretty simple. In first we obtain skills. In other, we train meta policy upon these skills. Okay. Now I'm going to describe how these skills are obtained, and to learn these skills, we train just a feed-forward neural network, but with following modification. We we give to the input of neural net not only S, but also some variable that will denote skills. Why exactly this architecture? Well, authors tried something like this, when you have state and when you have Z like this. But just empirically, this architecture performed better. Z is sampled from categorical distribution, that is, it's one hot vector, and all of these states will be zeros, and one of them will be multiplied by 1, and will be input to a neural net. Probably some of you can see some issue here in training of this neural network, or probably in training this neural net. Question is following. We want to maximize our reward. We want to obtain policy by A given S. What will prevent agent to ignore latent variable? Probably some random initialization will make it, but we have a tool to make agents not ignore this, and the tool will be mutual information. Recall our Z is uniform distributed. That is, entropy of Z will be constant. Other term will be expectation over Z and some variable C of logarithm of conditional probability. Here we will use C as coordinates, and we want our skills to be as diverse as possible. That is, we want for different Z agents to move in different directions. Yeah, and pipeline is following. When we have our episode, we sample Z, commit to it, and play with this Z whole episode. Then we receive sequence of rewards. We modify it by mutual information between this Z term and coordinates, and update our agent. with respect to modified reward. And thing to note is that we cannot analytically compute this conditional probability, thus we make some simple discretization, but in general we want to prevent ignorance of skills of latent variables z. Okay? And we train our skill network with respect to this reward. Okay? Now, when we have trained our skill policy, we in subsequent MDPs we train.
Here we're learning skills,
Okay.
but we do not have any guarantees that these skills are useful for the further tasks.
Yes.
Right?
Yes.
Because we're not using any kind of rewards from real world. Just
And
this mutual information.
Yes.
So in some sense, we're trying to learn
what
the
agent?
diverse set of skills.
Yes. Yes. What agent basically can do?
Yeah.
And experimental setting will be corresponding. Now, when we trained our skill network, we freeze it and train managing neural network upon these skills. That is, we will feed to managing neural network whole state space and denote its actions as z. Okay, and when manager produces some action z, some skill, agent is committed to it for some fixed number of steps, and then again state is fed to manager neural network and the process is repeated. Okay, and now I'll move to experimental setup. First Markov decision process. You have an worm, and your task is to move as fast as possible. You receive reward for agent speed. Due to mutual information bonus, it would learn to move into different directions. Okay, and in subsequent MDPs, you will learn to move from this position to this position. In here, you will learn to move from this position to another position, and in this MDP, you want to eat some green apples and not to eat red apples. And what do you want from? Okay.
Red and green apples and velocity or
again? We receive rewards +1 when we eat green apple and receive rewards -1 when we eat red apple. Otherwise, we receive rewards 0.
for minimum times?
Again?
For minimum times? Or
No. Just.
Only scoring?
But again, we have a discount factor that tries, in some sense, to solve MDP as fast as possible. Okay. And what do we want from this experimental setup? In Markov decision process 0, we want to obtain a diverse set of skills. In other MDPs, we want to train as faster than competitors.
Wait, but in MDP 0, you're also encouraging the speed, right?
Yes.
So there's explicit reward. We're not just training the diverse set of skills. We're
Yes.
also training to be as fast as possible.
Okay, and in this sense, we are trying, we teach worm to move.
Yeah. I wonder what happens if we do not use this explicit reward in MDP 0. If we just try to learn a diverse set of skills without encouraging to move fast. Will we learn something? Because we just can't learn nothing due to this mutual information criteria.
I guess we will learn something, but this speed up bonus accelerates learning.
Mm-hmm.
Okay?
Yeah.
Well, and we'll compare 4 settings. In first setting, we will use some simple policy, and others claim that in all of these MDPs, no speed reward is error, but it's really hard for agent to solve this. That's why they add speed bonus to make stronger baseline. Another setting is independently trained bunch of neural networks and manage a network upon them. And then we have stochastic neural networks with and without mutual information bonus. And in MDP, we can see MDP 0. We can see that we indeed learned diverse set of skills. Here is visualization of trajectories for different z's. I'm not sure whether. Yeah. Okay. When you do not have mutual information bonus, well, you learn to move up and down, basically. But when you add mutual information bonus with a large weight, you learn to move not only up and down, but to the other side too. That is, in some sense, we obtained a useful set of skills. And of course, stochastic neural networks with mutual information bonus are most sample efficient. You can see that red line is the best, and this is SNN with mutual information. Here's also, on average, stochastic neural network with the mutual information is best. Here it's comparable. Okay? Yeah?
Can you repeat what is iteration in top plots?
Here?
25 iterations, what is it?
I guess it's episodes that were well, in one iteration we collect a bunch of samples, a bunch of trajectories, and use the gradient update. I guess one iteration is one gradient update, but with respect to a bunch of trajectories. Okay? And if no one have questions, that's basically the last slide of our talk.
What about experiments on some real environments?
Well, nothing works yet in even this simple. On the first method, option critic, there was some experiments with Atari games, and they compared with DQN. But my guess is that this paper is 2016, DQN paper is 2013. They could take a much stronger baseline and well, best what they have achieved is they beat in DQN. That is, in some sense, it is able, but not to good solve Atari games.
But do they observe some meaningful options within these Atari games?
There was something on this, but honestly I don't remember, but I guess claims that these options are meaningful, but I am not sure that they are indeed meaningful. Because yet it's not working good yet. In this paper, well, this is a continuous control tasks, and they are benchmarks like targets. That's why it is quite serious. It's not that toy as it can be imagined. Well, this is benchmarks. Okay. Any other questions?
And what is your hope to improve this technique? What are you going to do with this?
Well, what I'm trying to do, I'm trying to make hierarchical but imitation learning, and I hope that it is a bit simpler task, and here options can really help to accelerate learning and to provide meaningful options.
Hierarchical, but
Imitation learning, when you're given a trajectory of state action pairs, but you don't have access to reward, and you want to imitate expert behavior. Okay, you have expert policy, samples from it, and you want to imitate its behavior, hoping that experts is making optimal decisions. Okay. Okay, and if no one have questions, here's the links for original options paper and for two algorithms that was discussed. And thanks for the thanks for your attention.
I would like to thank Evgenii for a very interesting talk. I strongly encourage everybody who missed something to review it again, because there are several important issues, especially in the beginning, the recap in general reinforcement learning theory and general approaches, as well as to review the two approaches to hierarchical reinforcement learning, because it is very likely that this will be one of the most important trends in reinforcement learning in the next years.